So, Physics 231C, course on classical mechanics. We're up to the 7th week of the semester. We're going to be studying Chapter 7 in the textbook. And the topic is oscillations. Mechanics is all about motion. And oscillation means something that goes back and forth. Those would be horizontal oscillations, or up and down, where there's the position as a function of time. Or it could be a pendulum, swings back and forth, mass attached to a string, which is attached to a point on the ceiling, or vibrations. So many examples of oscillations. Here's a kind of outline of the chapter. It starts with just a general definition of periodic motion, then a special kind of periodic motion, simple harmonic motion, then energy in simple harmonic motion. There's kind of a cute relationship between simple harmonic motion in one dimension and uniform circular motion in two dimensions, which is mentioned in section 4. There's a section on the pendulum. There's a little more advanced section on damped oscillations and driven oscillations. So in the screencast, I'll go over the first 5 sections. The 6th section is more difficult and more complicated. That would require a screencast of its own. So I'll just rely on the textbook for damped oscillations. So let's start with a summary. If we look at that last page of chapter 7, there'll be a summary. And so here's a kind of summary. First of all, there's a mention of periodic motion. It's shown here. Periodic motion is if you make a graph of, let's say, the distance over the time, distance versus time, it's repetitious. So it oscillates about some value of x. Or the motion between, the motion during oscillations could be different. It could be like this. That would be periodic. Or it could be sinusoidal. That's also periodic. So this defines what you mean by periodic. And then the frequency is 1 over the period. It mentions simple harmonic motion. That's where the position as a function of time, if you make a graph, is sinusoidal. So for example, one example would be position is A times cosine omega t, where t is the time, x is the position, the parameter A is the amplitude of oscillation. This quantity omega is related to the period of oscillation. The period of oscillation is 2 pi divided by omega. And the standard example of simple harmonic motion is a mass on a spring. You have a mass that slides back and forth attached to a spring. The other end of the spring is attached to an immovable wall, and the mass will oscillate back and forth because of the spring force. Then the angular frequency, omega, that's 2 pi over the period, is the square root of k over m, where k is Hooke's constant for the spring. It mentions energy in simple harmonic motion. There's kinetic energy, that's a half mv squared. And if this is the position as a function of time, then 1/2 mv squared is 1/2 m a squared omega squared sine squared omega t. And the potential energy for a spring is a half kx squared. So if this is the position x, I have 1 half k a squared cosine squared omega t. And now mechanical energy, the total energy, kinetic energy plus potential energy, call that E, will just be 1 half k a squared, a constant. So this little graph here shows, I guess, the blue, I'm making a plot of two different energies as a function of time. So this direction is time, and this direction is energy, which could be kinetic energy or could be potential energy, could be the total energy. The blue curve, I guess, is the potential energy. It oscillates between 0, so here's 0 energy, to some maximum value, 1 half k a squared. All right, so the potential energy oscillates back and forth between 0 and a half k a squared. The kinetic energy also oscillates back and forth between 0 and k a squared over 2. But they're out of phase. They're exactly 180 degrees out of phase. So where the kinetic energy, that's the yellow line, is a maximum, the potential energy, that's the blue curve, is a minimum, and vice versa. Or when the potential energy is at the halfway point, the kinetic energy is also at the halfway point. And as for the total energy, that's the green curve. The total energy is a constant. So the plot, the graph of total energy will just be a horizontal straight line equal to 1 half k a squared. There's a section on the simple pendulum, a little mass on a string. Little mass on a string. In Earth's gravity. So Earth is pulling this plumb bob downward. So there's a force of gravity. The string is pulling it parallel to the string. So there are these two forces which control the motion of the bob. And for small oscillations, that is to say where it doesn't differ, the angle doesn't differ very much from 0, the bob undergoes simple harmonic motion. The period of oscillation, the time to go from maximum angle to minimum angle back to maximum angle, is 2 pi squared of L over G, where L is the length of the bob, of the string. So there's an interesting fact here. The period of oscillation does not depend on the mass. A pendulum with a very heavy bob and a pendulum with a very lightweight bob will have the same period, always assuming that the string mass is negligible. What it depends on is the length of the string, goes like the square of the length, and the acceleration due to gravity, since ultimately it's gravity that's driving this motion. And then there's a section on damped oscillations and driven oscillations where the equations become a little more complicated and the functions involve more complexity. You have to use exponential functions because the oscillations will be damped out. They'll die down to 0. That's because of friction. Okay, so let's work our way through the chapter. First of all, periodic motion is a very general kind of motion. It means the motion is repetitive. the position of the object, and we'll just think about an object moving in one dimension. So here's the x-axis. Here's the object. Some mass. Think of it as a little object, a little particle, or just a little mass, a little object that's undergoing oscillations. So there'll be some equilibrium position, and this mass will oscillate back and forth about that equilibrium position. Some maximum displacement and some minimum displacement. Or that is to say, some positive displacement and some negative displacement. That's the oscillation. So if I plot x as a function of time, so here's x as a function of time, these are three examples of periodic motion. The plot might be a straight line followed by a straight line with negative slope, followed by a straight line with positive slope, negative slope, positive slope, negative slope, and so on. But you see how it's repetitive. So that's an example of periodic motion. Or it could be just a positive slope and then a jump down to the initial value. And then another positive slope and then a jump. And then another positive slope and so on. Well, that's again repetitive. And I suppose the most interesting case, which we'll spend a lot of time on in the week, is harmonic motion. Sinusoidal dependence of position on time. So this could be a sine curve or a cosine curve. So here we'll have to use some trigonometric functions like sine of the variable. Well, I guess the variable would be t, but you usually have to multiply by a frequency. So let's say sine of some variable, call it phi. Phi will be a variable proportional to time. Or it could be cosine. Cosine and sine are really the same sinusoidal shape. They just have a different phase. Just a question of where is the function 0? The sine is 0 at this point. The cosine is at a maximum at this point. So the cosine is sort of the sine shifted over by half a wave. Or actually a quarter of a wave. Now, this is pictorial. To make it algebraic, a periodic function has x of t plus t is equal to x of t, where t is the variable time. And capital T is a constant called the period of oscillation. So in this equation holds for all values of t. And capital T is a constant. What it says is, if I'm at some point and I look a distance t away, so if I consider this time t, and displacement of time, so this would be t plus t, this would be one period later, x is the same. So x is this value. X is this value. It's the displacement from the origin. Well, the displacement from the origin at time t is exactly the same as the displacement from the origin at time t plus capital T, or t plus 2 times capital T. Every one period, you've completed a cycle of the oscillation. Think of it as going from a node, a point where the position is 0, to positive direction, to positive displacements, then to negative displacements, and then you're back at the node. So actually, this is a node where the velocity is increasing, This is a node where the velocity is increasing, that is to say, is positive. This is a node where the velocity is negative. Remember, velocity is the slope of the curve. One complete oscillation is from the node, not to the next node, but to the second node, a node with increasing velocity to the next node with increasing velocity. Or maybe it's a little easier to visualize if you don't go between these points where the particles in equilibrium. Think of going from a trough or a crest to the next trough or the next crest. You know, it's oscillating, so it's got crests where x is at the largest positive value. It's got troughs where x is at the minimum displacement and the largest negative displacement. Well, from one trough to the next trough, that's one period. It's a complete oscillation. It goes from negative A up to positive A and back down to negative A, so it's a complete oscillation. Or just as well, you could say from one crest to the next crest. So it starts at A, goes down to minus A, back up to plus A. Well, you can see from the picture, if it's a periodic function, then the time from crest to crest is the same as the time from trough to trough. Or it's the same from node to the second node. All right, so this quantity t is a characteristic of the oscillation. It's the period of oscillation. It's the time it takes for the motion to repeat after one cycle. It's a time. So the unit of period is a second. You might have 60 cycles per second. That is to say, 60 times a second, the oscillation occurs. Or one oscillation takes 1/60th of a second. So that's period. Then there's frequency. Frequency is 1 over the period. So let's say the period is 1/60th of a second, then the frequency is 60 inverse seconds. Or you could say 60 cycles per second. Now that unit, cycles per second, oscillations per second, that unit is called the Hertz, named after the German physicist Heinrich Hertz, and abbreviated Hz for Hertz. The definition of 1 Hertz is 1 inverse second. So if the frequency is 1 cycle per second, then the period is 1 second. If the frequency is 1/60th of 60 cycles per second, then the period is 1/60th of a second. So that's the general description of periodic motion. Now, one example of periodic motion, one special case, is simple harmonic motion. Simple harmonic motion. And most of the vibrations that we encounter in mechanical engineering, or even in various science, chemistry or physics, is well approximated by simple harmonic motion. So simple harmonic motion is periodic motion, but of a very special type. The time dependence is sinusoidal. In other words, if you make a graph of the position as a function of time, the displacement from the equilibrium as a function of time, it'll be a sinusoidal function. So the example that they give in the book is A cosine omega t. That's a sinusoidal function. If I make a graph of this function, it's a sine shape. A cosine has the same shape as a sine. It's just that the point t equals 0 corresponds to a maximum for a cosine, whereas it corresponds to 0 for a sine. All right, so we'll take this as a kind of generic equation for simple harmonic motion. And you see it has two parameters. There's a parameter A. Now x has units of length, so A has to have units of length. A is called the amplitude, and the dimension of A is length. So the object may be oscillating back and forth between 1 meter and -1 meter. So 1 meter to the right, then 1 meter to the left, then 1 meter to the right, then 1 meter to the left. That would correspond to A equals 1 meter. Because the cosine oscillates back and forth between +1 and -1. So A times the cosine oscillates back and forth between A and -A. So that's a length. Then there's this parameter omega. Omega. This is the Greek letter omega. It is not W. Kind of looks like W, but it's not W. It's the Greek letter omega. That parameter is called angular frequency. And we'll come back to see sort of why it's angular when we consider the relation between harmonic oscillations and circular motion. But for now, just take this as a word. Omega is called angular frequency. The unit of omega is radians per second. Radians per second. Now the period is 2 pi over omega, because the period of the cosine function is 2 pi. The cosine function is repetitive. It repeats every 360 degrees. So the cosine has a period of 360 degrees. But we have to work in radians. We can't possibly use degrees. We have to use radians, and 360 degrees is 2 pi radians. So when omega t changes by 2 pi, omega t is a dimensionless number. Omega t doesn't have a unit. It just has units of radians. It's kind of an angle. When omega t changes by 2 pi, you're back to the same phase point on the cosine function. So to go from, let's say, from a crest to the next crest, that corresponds to omega delta t. Omega is a constant, t varies. One cycle corresponds to omega t equals 2 pi radians. So the period is this delta t, the time from one crest to the next crest, for example. So you see delta t is 2 pi over omega. That's the period. And the frequency is 1 over t. So the frequency is omega over 2 pi. Frequency has units of 1 over seconds, hertz, 1 over seconds. Omega has units of radians per second. And 2 pi here means 2 pi radians. One complete cycle. So the radians cancel. Omega over 2 pi has units of hertz. Oftentimes a student may get confused between the difference between frequency and omega. So, a homework problem might say calculate the frequency. And a common mistake is to calculate omega. And the numbers don't agree. Omega is 2 pi times f. Omega is 2 pi, a number approximately equal to 6.28, times f, where f is the number of hertz. Before we look at a physical example, a mechanical example, let's think about graphical analysis of this function. You know, we're interested in this simple harmonic motion, and we're taking as a kind of generic example of simple harmonic motion a cosine omega t. So let's make a graph of a cosine omega t as a function of t. So here's the t-axis. Here's the x-axis. T will be in seconds. X will be in centimeters. Could be meters, could be centimeters. Let's say it's centimeters. Let's say that A is 6 centimeters, just for the purpose of drawing a graph. We'll have to put in a value of A. Well, let's put in 6 centimeters. So in other words, the oscillating mass is oscillating back and forth between plus 6 centimeters and minus 6 centimeters. 6 centimeters is the amplitude of oscillation. And let's say it has a angular frequency of 1. Let us say 1 radian per second. And now let's make a plot using those two parameter values. Those are constants. T is the variable. So let's plot this as a function of t. Well, here's the graph. That's a cosine omega t. You see, it oscillates back and forth between 6 centimeters and minus 6 centimeters. It's at 6 centimeters. A little later, it's at minus 6 centimeters. A little later, it's back at 6 centimeters, then minus 6 centimeters. Then it's back at plus 6 centimeters. It's oscillating back and forth between plus and minus 6 centimeters. The average value over time is 0. So if I average the position over a long period of time, the average position is 0 because it spends just as much time in positive x and in negative x. In this graphical analysis, this distance on the graph is A. It's the height of the maximum displacement, or the depth of the maximum negative displacement. We plotted it for 6 centimeters, so A is 6. And now what about omega? Well, actually, it's not very easy to say what omega is in this graph, but it's easy to say what the period is. The period is t. It's the time to repeat. It's the repetition time. So, for example, from a crest to a crest, a maximum positive displacement to the next maximum positive displacement, that's t, the period. If I look here, here's a scale. So if I look here, it's about 6 and a little more than 6. It's about 6 a little bit more than 6, maybe 6.3. Actually, since the value of omega is 1, t is 2 pi seconds. Remember, t is 2 pi over omega. T is 2 pi over omega. I hope you're taking notes. Write that down in your notebook. The relation between angular frequency and period. And as for ordinary frequency, period is 1 over the ordinary frequency. But it's 2 pi divided by the angular frequency. All right, so if I take omega to be 1 radians per second, then the period is 2 pi seconds. That's about 6.3 seconds. And yeah, it goes from crest to crest in 2.3 seconds. Or from trough to trough. Or from one node, one rising node to the next rising node. That's also 6.28 seconds. All right, so I think I said these things before. The function cosine phi varies between plus 1 and minus 1. So x varies between plus a and minus a. Of course, 1 doesn't have a unit, but A has a unit. A is a length. So for this example graph, A was 6 centimeters. The period oscillation of cosine phi is 2 pi radians. That's 360 degrees. So if you think about angles, you complete one cycle in 360 degrees. So if you go around a circle 360 degrees, that's one cycle. In a few minutes, we're going to see the relation between simple harmonic motion in one dimension and circular motion, uniform circular motion in 2 dimensions. Well, okay, so 360 degrees, you have to convert that to radians. It's 2 pi radians. So the period of oscillation is delta t. That's change in time from one phase point to the next phase point. It's 2 pi over omega. It's where omega t is equal to 2 pi. So t is 2 pi over omega. Well, that's a graphical analysis, just mathematics. Now let's go on to a physics problem. And the physics problem we'll consider is a mass on a spring. So we have a mass which oscillates back and forth, sliding without friction on a horizontal surface. And it's attached to a spring. The other end of the spring is attached to a wall, an immovable wall. This will oscillate back and forth between an equilibrium position. And that has simple harmonic motion. So the mass on a spring. The block, let's say the mass is m, slides without friction on the floor. The spring, let's say it has Hooke's constant K, which is a measure of the strength of the force that it exerts, is attached to an immovable wall and to the block. Now we'll say the equilibrium length of the spring is L0. So if the spring has this length, L0, that's the equilibrium. At that length, the spring does not exert any force on the block. So the equilibrium length is when the force on the block is 0. But at time t, the length of the spring is some length L of t. So let's suppose I pull the block over here by some amount delta x. Then, or actually, I'm just going to call that distance x. So I'll put on the floor here an axis with a kind of a length. And the position of the equilibrium will be called length 0, or displacement 0. But if I move that over by some amount, that would be coordinate x. So the coordinate will be the displacement from equilibrium, not the displacement from this end. That wouldn't make any sense because that end, well, it's just a varying length. It'll be the displacement from the equilibrium. So at time t, the length of the spring is some L of t. And the displacement from equilibrium is the length at time t minus the length at time 0. So let's draw another picture. Let's suppose the equilibrium length of the spring is L0. I don't know, maybe that's 1/2 meter. And now let me move the block out here. Let me make a displacement x, maybe 5 centimeters. So, this might be 50 centimeters, and this might be an extra 5 centimeters. So X would be 5. The length of the spring would be 55, L0 plus X. So the displacement is the length of the spring minus the equilibrium length. Now, if I stretch the spring in that way, the spring will pull the block back. You know, that's the nature of the force produced by a spring. If you stretch it, it pulls back. Now, on the other hand, I could also compress the spring. I could have the block over here, and then the length of the spring would be less than the equilibrium length. In other words, the spring would be compressed. And if you compress a spring, it pushes back in the other direction. So when the spring is stretched, let's put the force in a different color. Let's put the force in, I don't know, blue. When you stretch the spring, the force is that way. When you compress the spring, the force is that way. It's called a restoring force. However you displace the mass, the spring pulls it back towards equilibrium. So if I pull it to the right, the force is to the left. If I push it back to the left, the spring will push it back to the right. So there's a restoring force, and it's this restoring force which causes the oscillations. All right, now to make all this quantitative, this is all qualitative. To make this quantitative, you have to know something about the force exerted by a spring. And that is called Hooke's law. Robert Hooke, a contemporary of Isaac Newton, they weren't exactly friends, they had a lot of disagreements. But anyway, Robert Hooke studied the forces exerted by springs and the forces given by what we now call Hooke's law. So here's the system we're looking at. The block sliding without friction on a floor attached to a spring. The other end of the spring is fixed. We have to know about the force, the potential energy, and the motion. So let's start with the force. The force is called Hooke's law. The force, since it's only one-dimensional motion, the mass only moves in the x direction. So I'll call the force F sub x for force in the x direction. And the strength of the force will depend on how much the block is displaced. So I'm going to move the block over here, and this distance will be x. So it's this axis. It's this number line with numbers labeled by x. And here's the 0. It's where the spring is not stretched and not compressed. If I pull the block over here, then the spring will be stretched. And the force will be minus kx. So the force will be negative. It's a restoring force. If I move the block to positive x, the spring will pull it back. Pulling it back means a negative direction of the force. So if x is positive, then the force is negative. And furthermore, the force is proportional to the distance. So the farther I pull it, the stronger the force is. If I pull it over to the right by 1 centimeter, there'll be a certain force. If I pull it over to the right by 2 centimeters, the force will be twice as great. You know, if I pull it over by 1 centimeter, the force will be K times 1 centimeter. If I pull it over to 2 centimeters, the force will be K times 2 centimeters, twice as strong. So the force depends on the distance linearly. And that's a good approximation for most vibrations. Now, X could be negative because I could compress the spring. I could move the mass over towards the wall. That would compress the spring. Then X would be negative because it's to the left of the zero. So on this number line, the positive values are to the right, the negative values are to the left. Then the force is positive because the force is minus K times a negative number. And minus times minus is plus. So this would be a positive number. So again, it's a restoring force. If I move it to the left, it's pushed back to the right. It's always pushed back towards the origin, towards the equilibrium point where the spring is neither stretched nor compressed. So that's called a restoring force. And the strength is proportional to the distance from equilibrium. So the strength of the force, that would be the absolute value of F, is K times the absolute value of X, the displacement, that's the distance. Now K here is a constant which is unique to this spring. Every spring has a value of K. And if you have 2 different springs, there'll be 2 different values of K. In other words, K is not some sort of universal force. It depends on what the spring is. It depends on what it's made of, how thick it is, how strong the steel is, how tightly it's wound, all that kind of thing. So K is not a universal constant. It's just a constant that characterizes the spring that you're talking about. That's called Hooke's constant. Or it could be called the spring constant. If you get a homework problem, you might find it gives you the value of the spring constant. That always means Hooke's constant. As for the unit of K, well, it's a force divided by a length, so it's newtons per meter. Force is newtons, X is meters, K is newtons divided by meters, times meters gives me newtons. So K has to have units newtons per meter. Of course, it could be expressed as newtons per centimeter or some other unit, but it'll always be a force divided by a length. All right, so now that's the force. Now the way we're going to study, or the way we're going to figure out the motion of this mass is using energy. So now we have to know what's the potential energy of a spring. So remember, potential energy is the energy of position. So it's the energy that varies with the position of M. The energy actually belongs to the spring. The source of this energy, the source of this potential energy, is in the spring, the steel that it's made of. And the potential energy for a spring is 1/2 kx squared. Force is minus kx. So if I made a little graph, we have space here. If I made a little graph of potential energy as a function of x, and here's 0. At x equals 0, the potential energy is 0. So that's where the spring is neither stretched nor compressed. That's the kind of reference point for defining potential energy. Then u at x is 1/2 kx squared. So it's a parabola. That's u of x. And remember the relationship between force and potential energy. Force is in the direction of decreasing potential energy. So if I'm over here, the direction of decreasing potential energy over here is to the left. So the force goes this way, back towards the origin. Or if I'm over here, the force goes that way, because the direction of decreasing u is to the right. So again, this potential with a minimum, that corresponds to a restoring force to the equilibrium, always toward the equilibrium. Now I have to prove that it's quadratic, a function of x. So let's calculate, let's prove that 1/2 kx squared gives me this force. Remember, delta U, the change in potential energy, is minus F when I make a displacement delta x. The change in potential energy is the work done that would be done by the force if you made that displacement. So that goes back a few chapters, but anyway, let's use that. I have delta U. It's 1/2 k x plus delta x squared minus 1/2 k x squared. Now I can expand out this square. It'll be x squared plus 2x delta x plus delta x squared. Think back to high school algebra. So here's x squared plus 2x delta x plus delta x squared, and then minus 1/2 kx squared. Now you see this term, 1/2 kx squared, will cancel this term, 1/2 kx squared minus. But then I'll have left 1/2 k times 2x dx. That's kx dx. And another term, 1/2 k delta x squared. But remember, delta x should be a very small displacement. So, you know, maybe I make a little displacement of, I don't know, a millimeter. Well, then delta x squared is negligible compared to 2x delta x. So I can neglect the delta x squared, and I can approximate delta U as kx delta x, because this only really is supposed to hold for a small displacement. When the displacement is small, the square of a small number is extra small, negligibly small. All right, now delta U has to be minus f of x delta x. That's the relation between force and potential energy. It's kx delta x, so f of x is minus kx. And that proves that that formula, 1/2 kx squared, is correct. All right, now we want to know how the mass moves. So let me tell you the answer, and then we'll show that it's correct. The answer is x undergoes sinusoidal oscillations. It undergoes simple harmonic motion. So x will be some amplitude a times cosine omega t. It'll turn out, we'll see that in a minute, omega is the square root of k divided by m. So the angular frequency of a mass on a spring is the square root of k over m, where k is Hooke's constant. The frequency is omega divided by 2 pi. So it's the square root of k over m times 1 over 2 pi. All right, well that's x. Let me also write down v, because I'm going to look at energies, so I have to know what's the kinetic energy and what's the potential energy. Well, I already know the potential energy. For the kinetic energy, I have to have v. If this is the time dependence of the position, then this is the time dependence of the velocity. It's minus a omega sine omega t. So the position is varying sinusoidally. And the velocity is also varying sinusoidally. But they're out of phase. They differ in phase. We'll see a graph in a little while. So if x is a cosine variation, then v is a sine variation. It's actually minus a omega sine omega t. We'll see that right now. We have to prove that. We have to prove that Okay, we're going to take simple harmonic motion and calculate the velocity. So again, let t change by a small amount, call it delta t. Then what's delta x? Because remember, velocity is the rate of change of x. So velocity is delta x divided by delta t. The change in the position divided by the change in the time. All right, so let's calculate the change in the position, delta x. It's a cosine omega at time t plus delta t. Or I'll write omega times delta t is epsilon, just to make the equations a little simpler. So I'll introduce a new symbol, epsilon, which is omega times delta t. So this is x at time t plus delta t, cosine omega t plus delta t, that's omega t plus epsilon, minus x at time t, a cosine omega t. Now, in high school trigonometry, I know when I was in trigonometry in high school, we learned how to calculate the cosine of a plus b. Cosine of a plus b is the cosine of a times the cosine of b minus the sine of a times the sine of b. So the cosine of omega t plus epsilon is cosine omega t cosine epsilon minus sine omega t sine epsilon. And that all multiplies a, and then I subtract a cosine omega t. Now remember, delta x is small, so epsilon is small. The cosine of a small angle is approximately 1. So I can make the approximation cosine of epsilon is equal to 1. Then I have a cosine omega t minus a sine cosine omega t. Those cancel. So this part will cancel this part. Then what I have left is this part. A times minus sine omega t times sine epsilon. So I have minus a epsilon sine omega t. Not really, I have a sine epsilon sine omega t. But if epsilon is a small number, then the sine of epsilon is approximately equal to epsilon. You know, the sine of 0.01 radians is equal to 0.01, to a pretty good approximation. So for small displacements, small angles, sine epsilon can be approximated by epsilon, just like cosine epsilon can be approximated by 1 for small angles. So this term becomes minus a epsilon sine omega t, approximately, but it's a good approximation for a small time interval. And epsilon is omega delta t, so this is minus a omega sine omega t times delta t. And delta x has to be v times delta t by this equation. V is delta x divided by delta t, so multiply both sides of the equation by delta t. Delta x is v times delta t. Well, if I look at the equation, v is minus a omega sine omega t. And that's what I have here. So this equation for the velocity is just obtained as a consequence of this equation for the position. If the position oscillates as a cosine, then the velocity oscillates as a sine, or actually the negative of the sine. All right, so these two equations are consistent. Now I want to show that the force and energy implies that this is the correct time dependence, sinusoidal. And that will prove with conservation of energy. The energy should be conserved. So if these equations for position and velocity give me conservation of energy, then I know this is the right answer. I mean, the answer is unique. It has to satisfy conservation of energy. So if these work, if these give me the conservation of energy, then I've got the right solution. There's only one solution. So let's write down the mechanical energy. That is to say, 1/2 mv squared, the kinetic energy, plus 1/2 kx squared, the potential energy. So kinetic energy is 1/2 m. V squared is a squared omega squared sine squared omega t. A squared omega squared sine squared omega t. And potential energy is 1/2 kx squared. So 1/2 k, x is a cosine, so a squared cosine squared. Now I have some common factors. Both terms go like a squared, so I could factor out a squared. And this is the relation between k and omega. I'm proving that. In order to make E constant, omega has to be the square root of k over m. And I know E is constant because conservation of energy for a conservative force. So since energy must be conserved, omega must be equal to the square root of k over m. Let's see why. Because m omega squared would be k. Omega squared is k over m omega squared is k. So I can replace the m omega squared by k. I have here 1/2 ka squared, sine squared, plus 1/2 ka squared cosine squared of 1/2 ka squared sine squared omega t plus cosine squared omega t. And sine squared plus cosine squared is always equal to 1 by trigonometry. Let's consider an arbitrary right triangle. So let's say this angle is theta. And the hypotenuse is, well, let's take the hypotenuse to be 1. Then this length is sine theta. Because the definition of sine theta is the opposite over the hypotenuse. You know the trigonometric mnemonic, so ka probably learned this in high school, toa. If you can remember this name, so ka toa, then you'll never forget the equations in trigonometry. Sine is opposite over hypotenuse. So sine of theta is this distance over 1, because I'm considering a triangle with hypotenuse 1. So sine theta is this side. Ka is cosine is adjacent over hypotenuse. So the adjacent is down here over the hypotenuse is 1. So this side of the triangle is cosine theta. And by the Pythagorean theorem, sine, the square of the hypotenuse is equal to the sum of the squares of the other two sides. So sine squared plus cosine squared is the square of the hypotenuse. The hypotenuse was 1. Sine squared plus cosine squared is 1. Sine squared plus cosine squared is always 1. By the way, if you didn't ever learn so ka toa, toa means the tangent is the opposite over the adjacent. So if you just remember so ka toa, you can never forget the equations of trigonometry. Anyway, that's not what I needed. What I needed was sine squared omega t plus cosine squared omega t. Well, that's 1. It doesn't depend on time. So E is constant. It's 1/2 ka squared. The only reason it works is because omega is the square root of k over m. But you see, if I say omega is the square root of k over m, then I have conservation of energy. That guarantees that this is the unique solution for the motion of the mass. All right. We can make a plot of x as a function of time and v as a function of time. So this axis is the time axis. It would be measured in seconds. I could use the same axis for x and v, although it's a little bit peculiar to do that because they have different units. Let's go back to the case where the amplitude was 6 centimeters. So this would actually be in centimeters. X is oscillating between plus or minus 6. It's plus or minus 6 centimeters. I should have said centimeters here. Here's the velocity. The orange curve is the velocity. Now, it has different units. I mean, it's centimeters per second, so I can't really compare the size of oscillations of velocity and the size of oscillations of distance. That would be comparing apples and oranges. You can't compare things that have different units. I can put them on the same scale, but it's the relative size here doesn't really mean anything. What would mean something is if I plotted the energies, then the kinetic energy would have the same units, joules, as the potential energy. Now we see they're both sinusoidal functions, but the blue curve, that's x, is the cosine function. So it's a maximum at t equals 0. It's at a crest at t equals 0. Now the sine goes from 0 at t equals 0. And it's negative, so it starts at 0 and then it goes negative. But then it oscillates again sinusoidally. If you remember graphical analysis of the position as a function of time, the slope is equal to the velocity. So in here, the slope is negative and the velocity is negative. But for this part of the cycle, the slope is positive. So the velocity is positive. And then the slope becomes negative again, so the velocity goes negative. So you see, they're both oscillating with the same period of oscillation, but they're they're 1/4 cycle out of phase. When the potential energy is a maximum, that is to say, when the displacement from the origin is a maximum, the kinetic energy is 0. That's where it doesn't move, at that instant when it's at a maximum displacement. There's an interesting connection between simple harmonic motion and uniform circular motion. And there's a little section of chapter 7 about that. Let me just show the picture. Suppose you have an object moving around a circle with constant speed. So that's uniform circular motion. Now project the position of the object on the circle down onto a diameter of the circle. Let's say the horizontal diameter. Project the position down to the x-axis. And then look at the position on the x-axis as the particle moves around the circle. Well, I've plotted down here the position on the x-axis as a function of time. So this is a kind of plot again where this is the direction of time. This is the x-axis again. You know, at this time, the position on the x-axis is here. So it's here. Now, as the particle goes around the circle, you see its position on the x-axis goes back and forth. So when it's reached this orange point, its position is here on the x-axis. When it reaches the yellow point, its position is out here. And as it goes around the circle from red to orange to yellow, then to green, then to blue and purple, as it goes around the circle, its position on the x-axis oscillates back and forth between plus r and minus r, and then back to plus r. where r is the radius of the circle. It's undergoing a periodic motion where the amplitude is r. And in fact, it's simple harmonic motion, because the projection onto the x-axis is cosine theta. But if it's in uniform circular motion, then theta is omega times t. It has a constant angle. No, it has a uniformly increasing angle. The angle, that's this angle, is the angular velocity times t for uniform circular motion. So the projection of the position on the circle down onto the x-axis is just cosine theta. Theta is omega t. So it's cosine omega t times r for the radius of the circle. So you see, that's exactly simple harmonic motion. So if I plotted the projection as a function of time, it would follow a cosine curve. And as I go around the circle many times, I go through many cycles of the harmonic motion. So projecting circular motion, uniform circular motion, onto a diameter yields simple harmonic motion on the diameter line. And the circular angular frequency, the angle is the angular velocity. So in circular motion, omega is called angular velocity. So the circular angular velocity, that's omega, is the linear angular frequency. That's the omega of simple harmonic motion. So that's kind of why this parameter for simple harmonic motion is called angular frequency, because if I compare it to the motion on the circle, it's just the angular velocity. All right, there's one more topic. Actually, there are two more topics, but there's another topic in this chapter 7 is a simple pendulum. You have a mass, that's called the bob, is suspended from the ceiling. So here's the ceiling. It's suspended from the ceiling by a lightweight string in Earth's gravity. So Earth's gravity is going to pull it down. But the string is going to pull it up towards the suspension point. A string can only pull an object. A string, you can't push something with a string. You can only pull it. So the string will pull the mass up towards the point where it's suspended on the ceiling. So you got these two forces controlling the motion of this mass. A downward force, which is always the same. It's always constant. It's always nothing but mg, downward. Its direction is always downward towards the center of the Earth. Then you've got the string tension, the strength of the force exerted by the string, which is connected to the bob. That is varying as the bob moves. Gravitational force is not varying. But the combination of this is periodic motion. Now, the mass moves on a circle. The radius of the circle is equal to the length of this string. So the mass will be undergoing a circular motion, but it's not uniform circular motion because the speed of the mass is not constant. But it is moving on a circle. And so you can define its position by the angle theta. this angle theta, the angle between the string and the vertical direction is theta. And for small angles, let's say less than about 30 degrees, theta undergoes simple harmonic motion. Theta will be some amplitude, theta 0, cosine omega t. The bob swings back and forth on the circle, and the angle undergoes simple harmonic motion. There's a frequency. Now, how does the frequency depend on, well, what are the parameters in the problem? The parameters in the problem are L, the length of the string, M, the mass of the bob, G, the strength of the acceleration of gravity. So you have 3 parameters here, and that will determine the frequency of oscillation. And at least for small oscillations, the frequency, I should say the angular frequency, is the square root of G over L. So for stronger gravity, you'd have a higher frequency. For weaker gravity, you'd have a lower frequency. So if you took this if you took this pendulum to the moon, and don't change anything but just take it to the moon, gravity is weaker, the frequency of oscillation will be slower. And it's proportional to 1 over the length of the string. So if you have a short pendulum, it'll have a higher frequency of oscillation. A big, long pendulum will have a lower frequency of oscillation. The frequency goes like 1 over the square root of length. I should really be saying angular frequency. But remember, frequency is just angular frequency divided by 2 pi. Well, the derivation of this result is something you'll have to read about in the book. But this result has 2 surprising facts. First of all, it doesn't depend on M. If you have a pendulum of length 1 meter and the mass of the bob is 1 kilogram, and you compare that to a pendulum whose length of the spring is 1 meter, but the mass of the bob is, let's say, 1/10 of a kilogram, they'll have the same frequency. They will oscillate together in complete phase with each other. That's a fact that was discovered by Galileo. It's not exactly true. It's true for small oscillations. But there's a famous story of Galileo observing a pendulum in the cathedral in Pisa, Italy. He was a professor of mathematics in Pisa, Italy. And he liked to observe motion, so he's observing the motion of a pendulum. The pendulum was a lamp in the cathedral at Pisa. So it was a very long lamp suspended from the ceiling of the cathedral. So, you know, here's a lamp. It's a source of light. And you can sort of picture Galileo reaching up and displacing the lamp a little bit and then watching it swing back and forth. And what he discovered was the frequency goes like 1 over the square root of L. So if he compared a large length to a small length, they would differ by 1 over the square root of L. The other surprising thing is the frequency doesn't depend on how far it's swinging. You know, theta 0 is the amplitude. Theta is varying between, let's say, 30 degrees and minus 30 degrees. But it could be 15 degrees and minus 15 degrees. Or it could be 5 degrees and minus 5 degrees. The frequencies are all the same. So you can picture Galileo in the cathedral making a small displacement of the lamp and then watching it swing back and forth. And then stopping it and starting again with a small displacement and watch it swing back and forth. And discovering that the period of oscillation is the same for large amplitudes or small amplitudes, as long as the amplitudes aren't too large, let's say less than 30 degrees. Okay, so the final section is on damped oscillations and driven oscillations, and I'm not going to include that in the screencast. Just do a little reading there. By the way, how did Galileo measure times? Well, you might say he could use a stopwatch. No, there weren't any stopwatches in the time of Galileo. In fact, there weren't any clocks in the time of Galileo. If people wanted to tell time in the time of Galileo, they used a sundial. There were no mechanical clocks or watches at the time of Galileo. In fact, it was Galileo's experiments on oscillators that led to the invention of clocks. Galileo himself tried to invent a clock, like a grandfather clock. It wasn't really all that successful. It was sort of the generation after Galileo that people designed the first accurate measures of time. So if he couldn't measure time with a clock, how did he measure time? Well, he had two methods. He could measure his pulse, and he could say, well, each pulse is a second. So I have 60 pulses per minute. And he counted the number of pulses to estimate the time. So that was one method. He used his own pulse as a clock. And the other method was, Galileo was musical. In fact, Galileo's father was a conductor of an orchestra for the Duke, the aristocrats who lived in Pisa. Galileo sang songs while he did his observations, and he measured the time of singing to determine the time that he was trying to measure. So, if he could sing 4 measures of a song, well, that would be 4 units of time. 6 measures would be 6 units of time. So Galileo made these remarkable discoveries, which led to the scientific revolution, which led to the scientific age that we live in today. But he had to do it with the minimum amount of measuring equipment apparatus. All right, so enough of that. You should try to do some of the line kappa problems now, corresponding to chapter 7.